cool. Thanks. Oh, cool. Thanks. Okay, nice. So auto transcription as well. So good. Then let me minimize myself. And let's start with presenting. So I'm happy that you subscribed. I don't know why you did it, because it's like hot Thursday evening in the summer, and like, why did you come? I still do not understand. But thanks. So that we can have this little discussion here. So basically, maybe let me, because I know none of you. So who are you? So basically, like, is it like data science program or whatever? So why you came here? So like, I mean, maybe just name, like bachelor, masters, whatever program, and like.
Now bachelor, part-time, and we're just starting with AI next semester, so we thought.
Perfect. Then today you're gonna be quite a lot of new things.
Yeah.
Yes, I'm Fabio, and I'm also in the same class.
You are all in the same class. Okay, good.
Part-time as well.
Then Fabio, okay, that's good. Yeah, all the rest doesn't matter. That's okay. Yeah. David. Okay, so David, Fabio, and
Laura.
Yeah. Sorry, just to pronounce correctly. I'm also not sure that you are David. Maybe you are David or like whatever you are exactly David. Oh, I mean, like how parents call you. So like this. But that's okay. That's okay. Okay, and this is closed. Okay. Good. So then let's have today this discussion. If you didn't have like any machine learning before, yeah, then I would say that today you're gonna have a lot of new things, yeah. But who cares? Let's go. So we will also check today. We will also check how well you understand in general what happens around. Okay, guys who maybe heard of machine learning in general. So do you know that there are generative and discriminative models? Okay, somebody says yes, somebody says no, no problem. So basically, these are examples of generative and discriminative models. So discriminative model, this is very easy, in fact, that finally you have some input data, and as the output, you have, let's say, the basic problem is classification. Yeah, let's go for very basic things. Imagine two classes. Yeah, and it means that what you need to do, you need to somehow draw a line that separates them. That's it. This is what all discriminatives methods do, in fact. So they all work with the same principle. Generative methods, they work a bit different. They are trying to understand how, let's say, your input data correlates with the one that is your output. Yeah, so it means that it is trying to learn the distribution, the joint distribution. I don't know, like, okay, you didn't have AI yet, but did you have mathematics? Do you know what is joint distribution? So because this is essential, that here it is just a joint distribution, here it is conditional probability. Yeah, so joint and conditional. And basically, yeah, this is how it works. So you need to know nothing more for today's lecture, because we're gonna be talking about generative models, and they're super cool, but you need to understand that we're gonna be not talking about the generative models that are like OpenAI, ChatGPT, or whatever. We're gonna be talking about different class of models, but in order now to check how well you understood what is generative and not, yeah, you can take your smartphones. I'm using it for the first time, honestly. I don't know how it works. So, I mean, I tested it at home. So basically, you can just, I think, type in your name and that's it. So because, they you to participate in a final leaderboard. So you're just getting your name. Oh, okay, Laura is here, Fabio is here. You see how it works. Okay, David is here. I can see one more guy who's, he's here. Okay, close here. So, and now I would start a questionnaire and you will have 60 seconds. So in order to answer to it, but I want to also mention that the faster you answer, in case people answer the same and it is correct, who answers faster are gonna be better, okay? So just to let you know. Okay, good. The question, model returns probability when you give it a data instance. Is this model generative or discriminative? Oh, here I can see how many people answer. Take your time, think. Okay, 4 out of 4. So I think that now, okay, good. So we have absolutely not clear distribution of people. Yeah. So now let's try to understand why this. So yeah, as I said, that one is like a joint distribution probability. Another one is conditional probability. Here I'm just saying that it is probability. So I didn't say which one. I didn't say that it is either the conditional probability, the joint probabilistic distribution. Okay. Yeah, if you just misunderstood the button, that's okay. Next question, you're gonna win. Absolutely no problem. Okay, good. So this is how it works. Then this is the question that is, I think, not for the points. Yeah, this is not a quiz. This is more now because it's very philosophical. So this is just for you. Like, what do you think? Can truly generative models generate new data instances? So yes or no? What do you think about it? So you can still, like, I think you have it, yeah? You have it there on your phones. Yes, 2 people already voted. I think now 3, 4. And now we see, ooh, somebody is alone. Yeah, somebody thinks that yes, others think that no. What is meant by these new data instances? So imagine what happens when, for example, let's say you might have heard about these GPT-like models. I mean that are generating the words. Yeah. So all these modern, let's say, models that are sold as the breakthrough in AI. You know what they are doing? They are just generating the next word in a sequence. Nothing else. Nothing else. So it means that to some extent they cannot invent for you a new word. This is the thing, yeah? So to this extent, it cannot create for you like arbitrary new data. It can pick up the from data points that already exist, yeah? The one that it seems has like the highest log likelihood, yeah? Like the likelihood to be the next one. So that's why I would say that, yeah, to some extent, yes, it can create like new data, yeah? But to call it exactly the new data, yeah? I would not call it like this. But still, yeah, it can create something at least. Okay, cool. Now, there is another question. How do you think if generative models can be used for discrimination tasks? So I mean that, for example, you have learned the joint distribution, and now I'm asking you, but still, can you classify the data? Because now I understand that you can generate the data, yeah? You can generate the data from these samples, yeah? So that you have like this sample of one part and sample of another part. But if you make the samples, does it mean that you really classify it, even if I know that you can make this sampling? I would say maybe it's even more philosophical question, but when now everybody answers, we're going to see. So 3, waiting for the 4th one. Okay. 8. Okay, so I don't know. Let's ask somebody. When? Because now I'm pretty sure that you have answered yes. Yeah, so I can ask. I can ask.
So it's basically the other way around when it can classify what is that when it can generate, it can also classify back.
Classify back.
So when it
okay.
knows what it's generating, it can trace back what it generated, so it can classify.
Oh, okay. So
we can go the other way around.
I see a logic. What you would say? Come on now. Okay, tell us how you did it.
If you have different classes, the distributions that you.
Okay. But then would you agree that it's done the same as Laura suggests, that you are like making the sampling and then you're making the back classification? So it's kind of working like this. Yes, very nice. So I would say another possibility is that if, for example, this is some task like, I don't know, again, this GPT or whatever stuff that you are generating, let's say, the next word. But you want, in fact, let's say, to classify what kind of text is in front of you in terms of classes. I don't know, like, this, you're going to have, I'm pretty sure, these tasks when you go to AI course about newspapers, I don't know, like the articles from popular journals, etc., etc. You can use the trick of taking such a code, the internal embedding or the bottleneck or the last layer. And then, so it means that you can use this model that was trained for generation, as a feature extract. So you can take, like, let's say, features, that it has at some point of its flow, and then to train this one as a separate classifier. So you take these features and you train it. So, like, basically, this is one of other opportunities if, let's say, your classification task does not relate to how you were training your initial task, So generative model can even help you with the other classification stuff, So it means that now you have learned somehow the data distribution. It means that you have extracted features, But then you can take these to the next step. Okay, so what type of models we're going to look at today? They might seem to be a bit complicated, especially when you have some conditional probabilities or whatever, but no panic, that's all good. Because this one goes a little bit before in terms of logical sense. So I think it was 2014 or whatever, such a code variational autoencoders appeared. Then it was 16, the generative adversarial network appeared. Then flow-based models appeared something like around 2017. And I would say good diffusion models, they appeared about 2021. Exactly, good, that you can take and, for example, get the image generation that you have now. This flow, and if you're interested more, you can just I'm gonna send then you a link to the presentation so that you can access all the links and just if you have questions during the lecture, also feel free to interrupt me and ask if you want to have something. So, but this is just in general what we have. Why do not we talk today about these GPT-like architectures? Because the topic of our lecture was initially something about generative models for images, And I would ask you in the end of today's lecture why it occurs that in principle autoregressive models and what we now were discussing, these generating new word, word after word, these are autoregressive, these are autoregressive models. Why they are not that good for images as the models that we're going to discuss. Because, I mean, imagine what it means to generate like a picture, an image with autoregressive model. In the basic scenario, I guess it means to generate pixel by pixel, So if you go pixel by pixel, pixel by pixel, Maybe you can do it something different. Maybe you can take some area and generate area by area. And in fact, in all these cases, the problem is going to be absolutely the same one that I hope you should understand by the end of today's discussion. That's why we're going to start with very basic and very simple. So I think the architecture that is called autoencoder gonna be one of the first that you should learn at your, if you have, I don't know, first machine learning, deep learning, whatever. So this is the first that you learn usually because this is kind of the basic idea that imagine that you have some data. In general, what you usually want to do with your data, as I said, that not like the final classification matters. Usually in machine learning, the good data scientist, he's trying to extract features. From whatever data he has, he's trying to get the feature extraction, and then with this feature extraction, you can already make different classification tasks. You can then provide, I don't know, also generative tasks, etc., etc. And autoencoders occurs to be one of the basic methods how to extract features. What it means to extract features. Your data that you get originally, usually it is quite noisy. Now I'm talking not only about pictures. Let's imagine just you as future data scientists that you have just a random data. Usually you have a lot of rubbish. Usually some of it is correlated with each other. Some of it has noise, etc., etc. So you are better to get rid of the unnecessary stuff, especially if you have a lot of data initially. And nowadays, it is very important to process all this stuff as fast as possible. Because if you have initially quite a lot of stuff, and then you want to have, about backpropagation, have you heard about it? Yeah, so in general. Okay, mathematics, a little bit of calculus. So basically, when you're going to be trying to train these models, what you need to understand is that here, all the intermediate blocks, these are linear algebra because these are matrix multiplications. So you are having different intermediate matrices, and you are trying, let's say here, you are making such a matrix paradigm that your next dimension is lower, lower, and lower. Yeah, and finally you're ending up in bottleneck. Here, you're going to be inside this decoder, you're going to have matrix, 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 matrix. That's going to finally return you back this lovely cat. This is linear algebra, and calculus going to be the point when you want to adjust the weights of these matrices, yeah? Because matrices, these are going to be some weights matrices. So how to get these weights such a way that whatever cat I give you, you're going to get the cat back. Yeah, for example, if we are talking about just the data set of cats. So this one you need to optimize and to understand that, these kind of matrices should work for cats, yeah, for example. And this is going to be working. So basically, this is autoencoder architecture. Make sense? Yeah, feature extraction. Then it occurs that we can quite easily turn it into the generative model. So what generative model should do? We already understood with you. It should be able to sample from some distribution. So it means that we should have idea that from our data, we can come to some distribution. And then from this distribution, we can somehow sample depending on what was the input. So this is what happens here. We make an assumption that, let's say, our cats as animals, when we are making this encoding, when we are making the feature shrinking, feature reduction, and getting this bottleneck, we make assumption that these cats, so like this intermediate layer, that all the data points that are responsible for cats, they live somewhere in a very, very narrow subspace, yeah? So that they live somewhere, and particularly, we make assumption that they live in some normal bubble, yeah? So that they are following some normal distribution. So like all the cats, when we are compressing them, let's imagine that now here we have compressed them to the dimension of 2. So it means that it's going to be 2 here and 2 here, because your normal distribution should have like the mean and variance, yeah? I hope this one is clear. Good. So it means that if we compress it to the 2-dimensional stuff, it means that there we're going to try to finally find for them kind of this Gaussian bell, yeah? So we're going to try to place them, not that they are spread through, because you understand, yeah? If I draw a plane, I can put dots here, 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 but I'm making an assumption. Okay, cats should live together, yeah? So it means that I'm making this circle, yeah? And in fact, this is a bell, and I'm placing their cats. So I'm trying during my training to make sure that they're somewhere nearby. And then imagine what I'm doing. So, I mean, after that I'm training, yeah? So here I have cats. So, and in fact, this slide was prepared by Claude. So he has provided a lot of cats because he was telling me that you need to be very careful if you are starting an Instagram account and if you just watch a couple of suggested cats, because, like usually Instagram is very biased. So if you are registered as a male, it suggests you only women on the beach and also animals. So I don't know why it happens so. And then if you choose, for example, animals, then there's going to be only animals. So Claude has chosen cats. And since then, he was getting only cats recommendations. So that's why these are cats from Instagram. So basically, you see that you can finally, I mean, you put one cat, yeah? But I don't know, maybe occasionally you get as a final output another cat, yeah, because your model is bad. So it is trying to understand what cat it was. And it is not capable of it yet. Yeah, it's like the initial stage, and then puts you like this cat or this cat or this cat. But now we mentioned that I want exactly my model to generate cats on purpose. So what I told you, we make sure that cats live in a circle. Yeah. So it means that what I can do, I can come to this circle and I can sample a point from here. Yeah. So if I already place all my cats in this subspace, and as I said, this is already a Gaussian belt with some mu and sigma, I can exactly sample from this mu and sigma. So do you know how to sample from distributions? You usually sample in distributions. I'm telling you that there is a normal distribution. What technique would you use, for example, for normal distribution? Normal distribution is quite easy for sampling, yeah? So how would you sample from normal distribution?
Mean and variance.
Okay. But then how would you generate it?
I'll generate.
Yeah, exactly. So the question is how you're going to generate it. So for example, I'm telling you that my distribution has mu 0 and, for example, sigma 5. How would I extract the data from such a distribution? How would I try to sample from this distribution? What I'm going to do? Have you heard of such a stuff that is called rejection sampling? That's absolutely no worries. That's absolutely okay. If you continue this lovely path and also visiting my lovely lectures, you're going to soon find out what is rejection sampling and in general, what are these cool tricks. So, I mean, think about it even today. I recommend you to come home and think about it, that if you know the distribution and I ask you to now get data from this distribution, yeah? I mean, you would expect, let's say, that your data should be, let's say, 0, yeah? If I'm telling you that you have a distribution of data 0, 5, yeah? So the mean is 0. You would expect that maybe it should be something around 0. But you know that occasionally it could be 5, occasionally it could be 3, occasionally it could be whatever, yeah? Basically with some smaller probability. So come home, think about it today, break down rejection sampling, and remember that I insist on you finding out what it is, because it's going to help you in the future. But here, I tell you, you just have a magic mechanism. You can ask me, yeah? Today you can ask me. I'm gonna bring you the data from this distribution because I know rejection sampling, yeah? And I'm gonna bring you some data from here, and then you're gonna decode this data and see the cat. Because we already make sure that cats live in the circle, yeah? Basically like this. Might be a little bit complicated, but just let me know if it makes sense. If not, ask questions. Then let's skip this slide, because this slide, I would say, is maybe the one that you would like to go in 2 years or whatever. So it is such a called reparameterization trick. This is about how I can make sure that I can take derivative there. Because if I have distribution, then it is a bit complicated to both sample from it and take derivative. But no worries. This one comes a bit later. This one, just to let you know that, in fact, you can make these generations such called conditional ones. So it means that you do not simply sample from this circle where cats live, but you also give some additional condition, let's say making a shrinkage of this area. You're saying, I want only orange cats. So you're just cutting the subspace of this space. And there we know that only orange cat lives. Yeah. So basically, I mean, these generative models, and especially this variational autoencoder is quite simple to train, in fact. So usually this architecture is not that huge, especially if your resolution of the image is not that high. It is quite straightforward and easy, because you see here, the model is very simple. And as I told you, here, in fact, inside just a couple of matrices. That's it. Yeah. So, is it clear? In general, what happens? Yeah, that there is this architecture that is encoding, decoding. Let me tell you in advance, 99% of the modern machine learning models that you now hear in terms of auto-regression or generating images or whatever doing, they have inside encoded and decoder architecture. I know only couple that do not have encoder-decoder architecture. Majority have it. And that's why when you're going to start learning about it, I would recommend you that you immediately pay attention to how this type of architecture works, because this should become your best friend. If you know this architecture, then it means that you're going to be cool data scientists. So cool data scientists. Now it's time for a quiz at the same link if you didn't close it. So get ready. And now I open the question for you. What is the problem of generating images? So this one, as I said, yeah, I was maybe expecting, think about it, yeah? So I was expecting maybe that you have kind of ideas about images, etc. But now, okay. So these variational autoencoders, what they are trying to do in general, they are trying to, let's say, make this kind of aggregation of the images that it has seen, yeah? So it is trying to understand it has seen this cat, this cat, this cat. So now it is trying to kind of give you an average cat, yeah? In fact, so it is trying to give you a kind of average. Ooh, okay, wow. Do you want to know the right answer? Wow, guys, I'm impressed. So in the slides, when you get this link, I have attached, I think, to almost every of this question, you're gonna see in the notes the link to, let's say, the answer where you can read more about this one. But here I can already tell you what I have told you, that variational autoencoders, they are work in such a case that we now have seen even in the video, yeah? That they were cats, 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 yeah? And as I told you, cats live in the same circle. So it means that we are trying to exactly kind of find, let's say, the aggregate cat from this circle. And it means that when trying to aggregate cats, what you're gonna see is that they're gonna be kind of noisy. So you're gonna see them a little bit noisy. So it means that it's not gonna be like a pure, sharp, cool cat. It's gonna be cat with some noise. Because it was tried to make the cat of aggregation. Okay, now, this is the stuff that I was maybe intended to, because now I understand that most likely, if you didn't have AI courses yet, it means that maybe you have no idea about what is PyTorch or TensorFlow or whatever, or maybe you have heard about it in general, that these are frameworks. These are frameworks that help you to train models. So you, being already after today's lecture advanced, I think that now you're gonna see that comparing to your group mates, you're gonna find out a little bit more new concepts, yeah? So you can already try this stuff out. Basically, there is like a Kaggle competition, for example, that is about painting like Monet. What is the idea? It has 300 images of Monet pictures. I'm pretty sure Monet should have more pictures, but okay, 300 is enough. And it has like 7,000 pictures of arbitrary, just photos of, I don't know, buildings, people, whatever. And the idea of this competition is that you need to extract, let's say, the style of Monet images based on these 300 and to put it on these 7,000 images. So it means that you should get a building in style of Monet. Very nice stuff. I heavily recommend you to do this. But again, as I said, that you can just take it as maybe boom, 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 running the cells, because I think you should know Python at least. Yeah, some basics of it. That's cool. Because then it means that you can run Python notebook. This is already good. This is already good. And for example, this one, this tutorial, this is like the official one from this competition. So it means that you can just run it through and see what happens, how it trains. Yeah, so exactly how the images change throughout the steps of training, how more and more Monet style is added. So it can just bring you more inspiration for the future work. In general, I think today it's also for you more about understanding if you are interested in this in future, or maybe no need for AI, you can change the problem, who knows, yeah. Maybe you still can do it, just think about it. And also interesting stuff about how to measure the performance. Because, you know, when you have like classification, it is clear that I can just measure. I know in advance what were the classes, yeah? So I'm just telling you, classify for me. You are classifying, I'm saying, oh, no, bad, 70% is wrong, yeah? Or I don't know, whatever. If it is like a binary classification, it's pretty easy. Or vice versa, 90% is right, yeah? You're saying, cool. How to evaluate the image classification? How can we evaluate that we made a great image classification? So you as a person, as I said, you, for example, would see, cat is blurry, yeah? Or, for example, cat has two heads, yeah? Something is wrong. So there are different problems with the generation, but here I have provided for you such stuff that is called like the possible measurements of the performance. I would say even like this first one is more interesting. So, I mean, you can just go there and see how it is done. So basically, let's maybe now try with you. You already now have enough knowledge to make your own metric for understanding how well we have classified, how well we have generated the image. So what we were discussing with you, you can extract features from images, yeah, basically. Let's imagine that we have done with you a separate model that is making like the image features extraction. Let's make something very simple, arbitrary. We have cats and we have many other pictures. We have trained with you some model that is classifying if in front of us it is a cat or not a cat, yeah? So, very easy. And then you remember what we were discussing in advance in the beginning, that when making, let's say, some even classification model, what you can do, you can extract some, let's say, layer. So, I mean, because you have initial data, matrix multiplication, then you get some intermediate data, yeah? Another matrix multiplication, another intermediate data, etc., up until in the end you have 0 or 1, which is classification, yeah? Let's now train this model on cats, yeah, and other random pictures. And then for cats, we're gonna then extract our last layer, yeah, for example. So we're gonna see exactly what are the features. So we're gonna look at the distribution of this last layer. So it's called differently. It's called sometimes bottleneck layer. It's called like pre-last layer, etc., etc. So the idea is that this is the last layer in your model where you have still features but not a final answer. So we can take these kind of distributions, yeah. So we can see how this vector looks like, yeah. And most likely for cats, it's gonna look some kind of a way. And now imagine what you do. You are generating a new cat already with the model that you have given to me. Yeah? I have no idea about your model. You are generating cats with whatever, maybe just drawing it. Yeah? What I'm going to do now, I'm going to give this image of your cat to this model that I have trained separately. It would extract features from your fake cat. Yeah. So this model is independent from your model. And then what I'm going to look like at, I'm going to look how this hidden distribution, yeah, let's call it hidden distribution of your cat is different from true cats, because I have true cats and I have distribution for them. I have features for them, this feature extraction for them. And I'm basically going to look if your cat is close to mine true ones or not. And if yes, then cool, congrats, yeah? But in fact, if let's say you have a cat with two heads or two tails or whatever, the feature extraction going to work differently. Yeah, so it's not going to put your cat into the same hidden space as my true cats. And the most popular metrics that are used for the evaluation of the image generation, they are based on this idea. They are based on idea of separately extracting features from the real images and then comparing these features from the fake images and seeing if it is close or not. Right? In fact, I wanted to talk a little bit deeper about the stuff that is called convolution, but I don't know. It is, of course, it is kind of a machine learning stuff, but it originally comes just from the map. Do you know the operation of convolution? Yeah. Oh, lovely. Then let's talk about it. So, do you understand what it means to make a convolution with kernel 1 by 1? Let's try to think. So you have a vector of your data. You have a vector of your data. What it means to, okay, now let's say differently. What it means to have a convolution with, let's say, the 3x1, yeah? So it means that you're going to have like this window of 3, yeah? It's going to be a kernel, and you're going to be sliding it through your data, and you're going to make the multiply sum operation, yeah? You're going to be multiplying weights of your kernel by your vector, like these 3 values of your kernel by the 3 values of your vector, summing them up, writing them down, yeah? Then again, multiplying, writing down, multiplying, writing down. So this is convolution, and that has not a kernel 1x1. But imagine that you have a kernel 1x1. What it means? It means that you're going to be just multiplying exactly by the weight that you have in your kernel. It is a single weight. You multiply, write down. Yeah. In fact, there is no summation operation. You just multiply, write down, multiply, write down, multiply, write down. But let me give you one interesting thing. In images, you can have several kernels. So in images, when you are making a feature extraction from images, you can have several kernels. So it means that one kernel would be responsible for, I don't know, extracting edges, yeah, for example, horizontal edges. The other one would occur to be responsible for extracting vertical edges, etc., etc. So when you have a kernel 1x1, this is kind of a trick. So it means that if your image has like several layers and you apply this kernel, you now might think what you can do with this kernel 1x1. So now just your intuition. Now there's going to be a question. Get ready. So it's going to be for your intuition. We will see how well is your intuition. Let's go. So why would you use this 1x1? Non-linearity, dimensionality reduction, or something about vanishing gradient. Yeah, maybe as long as I didn't tell you anything about vanishing gradient yet, maybe it has nothing to do with this. Yeah, so most likely I can give you a hint that you have only 2 options. Yeah, so let's go. Okay, already 4 people voted. So, ooh, we have diversity of opinions. So let's see whose party won. It won the party who decided to reduce dimensionality. So basically, what I was expecting from you. I already gave you now the hint that it's definitely not gradients. Forget about them. But non-linearity. You now told me what is the kernel. Kernel is multiply and sum. Non-linearity. This is where you have something different. I can tell you that summation, multiplication, these are linear operations. Yeah. So when you have your, let's see, linear layer, you remember that, yeah, like what is the formula that y equals a times x plus b, yeah, only multiplication and summation. So this is definitely not about non-linearity. This is about dimensionality reduction. As I tell you, you can have several kernels. And the thing is that if you use less kernels than you now have layers, you're gonna simply reduce your dimensionality. So this might be, let's say, a bit now not that clear, but definitely it's not non-linearity, yeah? So that's why this goes away, this one is correct. Ooh. Yeah, please.
Just question, because I picked the correct answer.
Yeah, oh, that's great.
But I would
Okay.
like to know if my reasoning was correct, because I thought if you have, let's say, a curve that can determine, maybe have a horizontal, so therefore it can't be vertical edge. So that's why we have a reduction. Because
Could you please say once again, so about vertical and horizontal?
So that's how we have a kernel that confirms that we have a vertical edge.
Yes.
So therefore it can't be a horizontal edge.
Yes.
And that's why we won't need to look at other kernels that contradict this. And that's why we have a reduction of dimension. Or is this the wrong way around?
Not really, not yet. So the thing is that, first of all, the kernel that would be responsible for, let's say, edge detection or whatever, it cannot be the kernel that is of size 1x1. Because the one that is responsible for edges, let's say, it should be looking at the bunch of pixels, yeah? Yeah, it should compare exactly. It should look at several pixels and see if there is a change in the gradient, yeah, kind of like this. So that's why your idea might work in case of not one-by-one convolution pixel, yeah? So because you're gonna, so it means that you're gonna only, let's say, you as the one who proceeds with the task, you're, let's say, only interested in understanding if there are horizontal edges. So it means that you're just gonna apply this particular kernel, and you're gonna forget about the rest. Yes, by this, if any prior analysis was done, yeah, for example, or if you have like the image that has the dimensionality of 3 layers, you're gonna immediately reduce this dimensionality. Yes, to this extent it would work, yeah. But in the case of one-by-one, a bit different. But that's okay. As I said, you are still young and beautiful, so everything is ahead. So just let's try to understand what else there is. Guys, as long as you are, as now we figured out, are still our future. So this website is for you. It's called developers.google.com, and then it's called /machine learning. I mean, ZHW is a great university, yeah. So, but if you want to, you understand that if you want to read something more, you are better to also study something by yourself. Yeah. So let me just maybe even okay. No, you can get at home. Come on, I won't give you spoilers, but this is the best self-study resource that I have ever seen. If you only begin machine learning, so it's not about no. Remove this part, GANs, it's not yet for you, yeah, but there it's gonna open for you the starting page, and there is such a stuff that is called machine learning crash course. Trust me, going through this course would put you as the #1 among other guys who didn't come for today's lecture. So exactly this one gonna save you, I mean, because that I know, and Google also has these kind of asking you in order to make sure that you understand it, etc., etc. So this is the most important slide for you today. So just is developers.google.com/machine learning. Try to finally see what there is else. Another way, except from the inspirational autoencoders, is in fact also quite simple idea. It is very simple idea. Imagine that you have now you remember, yeah, that we were like training, particularly let's say on cats, yeah, and we were then extracting cats. We were sampling not from random, yeah, but from some sub area. Yeah? Here we can also do this stuff, but in the very beginning. I'm in the very beginning gonna give you, let's say, the vector that I'm gonna ask you sample me from Gaussian distribution. Just from some Gaussian distribution, sample me. Then pass this noise. Now it is noise. You put some generator, whatever architecture, and then you just get, let's say, the fake image here, which would initially look like this. And this is the true one. And you're going to have a separate network, which is taking the real. What is this? $10. I don't even remember who is this on $10. Do you know? Shame on me. I mean, I'm pretty sure on $1 it should be Washington. On 100 it should be Franklin. On 10, no idea. So you see, I was also not that much prepared. But in general, so you have a separate operation, you have a separate network that takes then what you have generated, what is the real one, and it should try to classify if it is fake or true. So in fact, I would say this architecture from which one we have today, for you as, let's say, the beginners in the data science, this, I would say, GAN is the most straightforward architecture because it has this separate data, because now you're already familiar with this idea of sampling, yeah? That you can have like this, whatever, distribution, yeah? And there we were exactly training this distribution of cats. Here, I would just ask you, give me a sample from distribution, just keep it the same. I mean, keep the same distribution. Every time you're gonna sample different stuff, but distribution, I don't want to learn what is this distribution. Just tell me, let's say, that it is Gaussian distribution 0, 1. Okay, cool. I'm gonna be sampling from this distribution, yeah? So because I have particular task of generating, let's say, the images of money, so that's why I'm gonna be using just this tree distribution for the money. If I'm gonna bring another image, this already won't work because I exactly was sampling from this distribution in order to generate money. Yeah. So here before cats were defining the area. Yeah. And here vice versa. I'm first choosing the area and then I'm trying to convert this area to bucks. This is how it works. Yeah. So basically, you're going to take the samples, you're going to make this generation and the separate model that is then trying to discriminate this stuff. So the question is it hard to train? And I can tell you in advance, very hard. So this architecture, why? Because it has two models that are competing. And the key problem, and I think this one you can already understand, that imagine, initially, when I give you just a noise, and you are trying to throw me something, looking at this noise, yeah, you can think of this noise as of a sketch, yeah? I'm giving you a sketch and saying, convert this to $, yeah? You have no idea initially how to do it, yeah? So it means that for discriminator, for the other model, job gonna be very easy because it has the true bugs that look exactly like bugs. And I have your piece of art that looks like that, yeah, originally. So that's why for a discriminator, it is pretty easy job. And most likely, if you do it not well, yeah, if you do it for the first time, and I would say this is what I hope you're gonna encounter. You're better to have these kind of mistakes in order then to understand how to deal with them. You're gonna most likely have no training at all because simply discriminator, it acts the last one. So, you know, in machine learning, there is this kind of paradigm that the one who acts the last one is more important. Because first, we are taking his model for update. We are trying to understand which direction his model to move. And then we are trying to move the models that come before. So this is exactly the problem that you're gonna then find out that was on slide that is called vanishing gradient. Yeah. So basically here, there are going to be no gradient at all because our discriminator would be originally so cool that we just wouldn't need to update it. It already can distinguish shit from real money, yeah? So that's why there are going to be no kind of trend. So that's why I'm going to leave these links to you. There are a lot of opportunities how to deal with it, how you can make such a called alternating training. It means when you freeze one of the models and then trying to train the others, you are saying, like, come on, yeah, produce something good. Then you say, stop, yeah? Now you try to tell me who is right, who is wrong, yeah? Who is fake, who is right. You train this model, then you can freeze it and train. So there are a lot of methods. You can go through them with these links. Yeah, please.
Is the goal that
Sorry?
at some point the model will create pictures that the GAN cannot distinguish?
Exactly. The cool question. This is the idea of this training. So the idea of this training, thanks a lot for this question. Let's come back to this slide. So the training would stop ideally when this guy gives you 0.5 probabilities. When it cannot understand if you gave me like the real picture or the fake. Yes, this is the final idea. Absolutely. I'm just gonna show you a couple of architectures that are now modern and still are used. But you know, let's be honest, modern, it means that I don't remember, maybe this one appeared like in 2018 or whatever. So the next one appeared like maybe 1 year later, but the truth is that they are still heavily used with some additional tricks. So these are basic architectures, but with some additional interesting trainings they are used. So this is just for you. I would say maybe here, yeah, there is this architecture that you first get generation, and then what you are trying to do, you are trying to bring back. So first you generate it, then you are trying to shrink it and bring back. This is the idea. This is why it's called cycle GAN. So you are kind of doing this reverse cycle. So you are first like trying to classify it, but then you are trying to reproduce it. What is the idea behind this, and what you would, I would say, like to learn from this? That in general, there is such a stuff that is called cycle loss. So, for example, this is what guys are doing in our lab, who are working with texts, and then who are finally, so what they are doing? They are doing the natural language to SQL. They are trying to do such a model that's gonna be simply taken like arbitrary human question and converted to the SQL depending on what it should be like. Yeah. And here, the problem that comes that it's not clear how to measure how well I have done it, yeah? Because, I mean, you could create just an SQL that is perfect one, yeah? It exactly would extract you what you need. Or maybe you have made a little mistake and it's gonna extract a little, for example, or vice versa, a bit more data, or it can extract totally different data, yeah? And in these terms, it is not clear how to identify what is good, what is bad. And what they are doing, they are cycle loss. So it means that they first make natural language, natural question, yes, so just a person question to SQL, and then they are doing back. You are doing the model, the second part that is bringing back from the SQL to the question. And then they are measuring how this question is different from that question that finally was at the end. Yeah. So just keep it in mind that this is the idea that you might use when you are absolutely not sure, like how to measure the quality of whatever, let's say, prediction. Yeah, you might make a second additional model that brings this data back, and you are comparing it. In fact, you see that this is kind of idea of autoencoder. Yeah, you have already seen it. In fact, everything is bringing back. So this encoding, decoding, autoencoder. So this is, I would say, kind of the example of how autoencoder is implied inside the GAN. Yeah. This stuff, let's not discuss it today. I would say that this is kind of basically this idea. In fact, you are already familiar with it. Now I told you that we're going to be giving a random noise, yeah, in the beginning. I just need to fix the distribution from which I'm going to be sampling. But every time I'm going to be sampling just from whatever defined distribution. But guys who invented such a code style GAN, they did slightly differently. They said, okay, but now in VAE, in variational autoencoder, there was an idea that we are kind of, cats are defining the distribution where they live, yeah? Here, they made the same thing. They have taken the pictures of people, so this model, it works originally on pictures. And basically what they have done, they have trained the separate model that was making classification if, let's say, person has beard or not, if he has glasses or not. Yeah, for example, now you two have glasses. Yeah, for example. Yeah, I also have glasses somewhere, but now not on me. And what's there is one. What I should
press any button.
Yeah, any button, but where?
On the TV itself.
On the TV. There is no button on TV. Jesus Christ.
How did you turn it on?
It turned on automatically. Just when I inserted this one. Oh. You know, your idea still doesn't work.
Just keep it running. When it turns off, plug it in again.
But maybe we can do it exactly right now. Just plug in, plug out. I think it is a good opportunity for me to turn on the charger. Otherwise, we're going to not have this lecture for long. But meanwhile, plus minus okay? Plus minus clear? Oh. That's okay. So, hey, come on, get away. So, here, the idea that was used, it was absolutely already familiar to you. So they have trained a separate model that was, as I said, predicting like glasses or not, if there are mustaches or not, I don't know if it is a woman or man, etc., etc. And then from this trained model, it was a model that was multi-class classification model. So in the end, you understand that I can put only 0 or 1, or I can put a vector of 0, 1, 0, 0, 0, 1, yeah, depending on what features you are trying. So you can make like multiple predictions. It's called a multi-class classification model. And from this model, what they have done, they have extracted the pre-last layer and they have put it as a noise, kind of this. So basically, they were trying, I mean, this is not how they done, in fact, but let's think that is how they done because it's very close to what was done. So the other pre-trained model, this was exactly extracting the style of the images. And then your model was generating according to what style you want to have, yeah? So you are basically exactly trying to extract the style and putting the style as the initial random noise. So instead of initial random noise, you're putting style that was extracted by another model. And it was quite cool. So if you want, you can go to, so you see here, I also attached different YouTube links. So you can just go to these links just for fun, because maybe you do not understand how the, let's say, math behind or the architecture, but at least it's going to explain to you how it is done conceptually, yeah? Because I think today you already know some conceptions. So I'm sorry, again, we need to practice. So let's go. Which of the following cannot appear in GAN? Okay, we have time. I can explain to you. Vanishing gradients, yeah? So as I told you, the problem that sum is trained, then the closer we go to the beginning, it already doesn't work. Failure to converge. So it means that it is trying to generate something, but nothing happens, yes? So it means that it cannot train. It cannot train, basically. Mode collapse, it means that it continues generating the same stuff. So you gave it like, I don't know, different money, but it's continued generating Benjamin Franklin. So for some reason. So basically, these are the problems that might appear. And the question is, from what we now have discussed, which one can be a problem for GAN? Okay, I see that all four answered. And I would say that's pretty good distribution. Failure to converge. Yes, obviously. Yeah, we discussed this stuff that it could be hard just in general to train, but vanishing gradient. Yeah, I understand we were not yet discussing it, but exactly this is the problem of this gradient that is less and less important as you go to the beginning of your network. And mode collapse, GANs, exactly because of this stuff with how the classifier works. If the classifier, so I mean, just imagine that you are a generator in this GAN architecture. What is the easiest stuff for you? The easiest stuff is to perfectly draw one type of picture. So what you are doing, you are simply perfectly drawing $10, don't care about the rest, because you know that discriminator is gonna give you 0.5, 0.5. Yeah, so that's why this stuff with faking discriminator, it has also this drawback that if you do not use other tricks that were mentioned at another links, then you're gonna have such a called mode collapse. Okay, cool. So this was the right answer. And now, I'm sure that I want to discuss it now, but guys, I'm pretty sure you know what is inverse function. You know that there is a function, you know that there is an inverse function. Forget about machine learning. Let's just think, if we are doing not this encoder-decoder stuff, but if we first apply functions that are somehow making feature extraction, and then we apply inverse functions, it means that we're going to be able to perfectly reconstruct our data. I mean, like, this should be the logic, yeah? That if we first like encode it in the function f, then applying then f minus 1 should perfectly give us the right. This is the model that was developed, I think, by the way, 18th is correct here, or maybe 17, something like this. But this occurred to be very complicated mathematically. So, I mean, that even guys from data science community, they said like, okay, too complicated. So that's why, I mean, I no, okay, no, let's not talk about I. Let's just answer this question. And maybe for you, it's going to be obvious answer. I mean, it's not a quiz. It's just, have you heard of it or not? So I'm just interested. I'm just interested in general, because I mean, obviously you have heard, as we discussed about, let's say, GPT technologies, yeah, or whatever. But now, boom! I was thinking, wow, this is the most unexpected answer. Because me myself, I used it only once in my life. I think exactly when they appeared. So it was a big hype. Everybody was suggesting to use it. I also tried it out to the work that I was back then doing. And then I understood that, okay, thanks. But you're also going to see it on the last slides that, in fact, there are itself, these models, they are not used that much. But there are, for example, VAE inspired with flows. There are, if I'm not mistaken, autoregressive models with flow. There are GANs with flow. So I mean that I think almost all the types of the models that we have seen together today, they have this idea of flow as well. They have this modification. So that's why itself, these occur to be not as viable, but it is sometimes used in the combination with others, just as a part, as an idea, let's say, as in coding and coding. Okay, good. Exactly. This is absolutely support you guys. Yes, I was waiting for this sound since the beginning of the lecture, because here without beer, it is hard to understand. I absolutely agree. I should have brought alcohol. Okay. Oh no. Because this is, I would say, the main important model which I would like to discuss with you today. It is a diffusion model, and behind all these generative approaches that you now see, for example, this DALL-E, yeah, or if you were using, let's say, ChatGPT, and there, if I'm not mistaken, now even in the free version, you can get the image generation, or maybe not. Sorry, I do not remember. But basically, behind this stays diffusion. Neither VAE nor GAN nor whatever flow architecture I use, it is diffusion. But diffusion, again, today we're discussing many things on the conceptual level. On conceptual level, diffusion is very easy. Imagine, and I think, I would say diffusion is a good example of how you need to think being a data scientist. Try to think differently, even from the point, let's say, of what you are predicting. Yeah. So, for example, people are telling you need classification. Yeah. But then you see that classifying is, let's say, too complicated, but maybe you can do, I don't know, generative model that can later be converted to classification. Yeah, for some reason you see that it is easier to be done. Boom, you do it. Here, it is the same. So as you see before, we were always trying to predict the picture itself. We were trying to generate the image itself, yeah? But here, it occurs that we can do totally different idea. Imagine that we are trying not to generate the image itself, but we are trying to say that if I give you just a piece of noise, what noise I should extract from it in order to get a picture. How it is done. Just let's think about it. How the training is done. I'm giving you the picture, that is true one. Then, in several steps, I'm adding their noise. So do you understand what it means to add noise? Add noise means that you are just, let's say, it is here, I think, demonstrated pretty well what it means to add noise. It means to corrupt pixels, yeah? You are corrupting pixels. But this corruption, it happens with Gaussian distribution, yeah? Our favorite for today. So basically, you are somehow, let's say what you are doing. You are extracting from Gaussian distribution and simply adding it to the image, yeah? You can summation, yeah, basically. So you're just making a little bit of corruption. Then boom, 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 dog occurred to be now a total noise. The same for the person, yeah? And now, imagine what I'm gonna do for you when it's gonna be already the prediction. You're gonna just take this random noise, you would provide me random noise. And you are going to tell me that, okay, my model, in my original model, there were 100 steps of adding noise according to some formula. Now, can you exactly tell me that if I now generate, so I mean that obviously for this man, there was this noise. I don't know, for dog, there was whatever noise. Now, I'm going to whatever noise, and can you tell me which noise, for which picture corresponds to this type of noise? Yeah, let's say the final noise. So it means that what you're going to be doing, you are going to be step by step getting rid of noise, because I mean, you know the formula, how the noise was created, yeah? So it means that basically, and I mean, by the formula, I mean that you know that it was Gaussian noise, yeah? And then what you're going to be doing, in fact, like on the stage of like training and then prediction, you're going to take the original image. You're going to take the picture with noise at step T. You know this, it is very important. So this model, it is very important that you know how many steps you have done. So here you would take this T. So and then you're going to have here some kind of neural network that's going to predict you how much noise you should remove from this step in order to get a dog. Okay, so it means that because here, obviously, you have the original picture, you have a dog, you know the step, you know how much noise was added, you exactly know the noise picture, yeah? You know the noise picture that was additionally added to this dog. And what you're trying to predict, you are not trying to predict the dog itself, but you're trying to predict the noise. And this was the revolution. In general, in the machine learning models, it was a revolution because as I told you, yeah, before we were taking the noise and trying to generate the image. But now we were taking the noise and trying to understand how much noise we should subtract in order to get the picture. And we were exactly predicting the noise. And this is what is done in the diffusion model. Makes sense? Yeah, so that's just very different concept from what we were discussing before. I mean, still in all the concepts we have noise, but to have such a case that we are predicting from noise how much noise we need to subtract, this is something absolutely mind-blowing. And just to let you know that for this one, there is a special architecture that is used. I think there is no need to go now into depth into this architecture. Just to let you know that this architecture is was used for this because it keeps the same dimensionality of input and output. So just because of this, just because of how it is done here, and you see convolution one by one, you're already aware of it. And you wanted to make some feature extraction, yeah? For you, it is 3x3. This is kind of making this feature extraction. And yeah, there is a lot of additional stuff, and there is a lovely YouTube video that I found especially for you. It is called UNet Explained in 10 minutes. So yeah, when you're ready for this, please allocate 10 minutes of your time and get it. So now, modern architecture, because as you see, I'm trying to show you the state of the art in every model that we now have. Don't pay attention to this stuff. There is like, I don't know, QKV or semantic mapping. Nobody cares. What is the most important difference from the original article about diffusion and the diffusion that is used now in the modern different APIs that you might use? Is that instead of analyzing the picture of, let's say, dog and dog with noise, yeah? Dog and dog with noise, you are introducing here a little encoder-decoder. So, because basically, you see, as I told you, very popular concept. At some point, it occurred that diffusion is very slow. It works. Yes, it works. But when you have a picture 1000 by 1000, it occurs to be very, very slow, taking into account that the normal time step that you need to do is also 1000. So it occurs that good diffusions, they work if you edit noise in 1000 steps. And then imagine that you have 1000 by 1000 pixels, which means a million. Yeah, so which means a million. And just you need to process million with 1000 steps. So it is already on the order of billion. Yeah, and then you have many parameters. So I mean that it occurred to be so slow and bad that some interesting that, if I'm not mistaken, these were the guys from somewhere from Germany. So this was a rare case that I think it was not guys from Google. Because I think like the majority of the modern models that we were discussing with today, they were originally developed somewhere either in Google Brain or in Google AI or whatever. But this stuff, I think, was developed not there. And this is really cool because too big images to process. In order to make it more stable, because of like many steps, let's work with the small copies of them. So they just made encoder and decoder. So basically, they took this big dog that is 1,000 by 1,000, they converted it. They trained a separate model that converts this, even not separate model, but okay, sorry. Decoder would be a separate model, but in general, so you work with smaller dogs. You are making this noise prediction for small dogs, and then you're just making the dog bigger. So there is a separate step that is making your dog bigger. But in fact, in order it occurred that in order to subtract the noise, you don't need a big dog. For subtracting a noise, you just need a small dog with noise, then to understand this noise, and then basically what you, this is very important idea also, that, for example, working with small image, it's much easier, but then what you can do, you can build a separate model that is called image enlarger. So you just gonna make the image bigger in higher resolution, and there is a separate procedure that is called sharpening. So when you're taking a smaller picture, you're making bigger, and then you're sharpening it. And this works much faster. It works more stable. And since then, this is the state of the art that is basically used. So it is working with lower dimensionalities, and then finally separately making the bigger dimensionalities and making it look a little bit better. So, sorry guys, still competition is continuing. Let's see. Boom. Complicated question. Which trick helps to make an inference in diffusion models? So, we have discussed with you now that I told you about UNets. I told you about the noise. I told you that noise is added according to some formula. And it is clear that original image is definitely not a Gaussian noise, yeah? It has some other distribution. But now think, what exactly helps you to make the prediction, yeah? So what exactly helps you to make this step that you are taking total noise? You are trying to say like what was the original image, but in fact you're gonna not do it like this, but you're gonna then make this noise subtraction and addition. So you're gonna be making noise subtraction and addition. Subtraction and addition, it should give you to one of the answers which has something about noise. Come on! Oh, Jesus Christ! No. So, I'm sorry. So, this is the right answer. Try to talk about subtraction and addition. Subtraction and addition. Yes, so like this is some. So, the thing is that your network, the one that we were looking into, it would not immediately tell you that, you give me total noise. This is the dog. Yeah, that was original. No, of course, this doesn't work like this. You would need to do it step by step. Yeah. And this will work exactly through like trying to get rid of noise, then like getting back, again trying to get rid of noise, then getting back, as I told you, because you know the formula. Yeah, you know the formula. But knowing the formula does not make the trick. Knowing the formula just exactly tells you that this is gonna be Gaussian. Yeah, that this is gonna be Gaussian. But exactly making these steps, this is possible because of the Gaussian distribution. The sum of Gaussian still stays Gaussian. So it means that if we are making subtraction and addition, we are still staying in the Gaussian noise subspace. So this is, I would say the question itself is quite tricky. And I'm happy exactly we're choosing between those two. Because yes, in terms of, I would say that this one, should be the answer if I ask you what helps to make the training. If what makes helps to make the training, yes, it helps exactly that how the noise is added. Yeah. So, but exactly in order to make the inference, because it is like hard to be done immediately. Yeah. Then it's going to be done through the summation and subtraction, but that's okay. All right. This is as the sum up in general of what we were discussing today, you can at the source where I took it, very popular image. As you see, there is no flow-based models. So there are bias, GANs, and diffusion models. And basically, the main limitation of diffusion models that is claimed here is fast sampling. But trust me, even this is already solved. So I mean that particularly, I would say that nothing should stop you from using diffusion model instead of something else. Other things could be used for the training, yeah, for you to understand the concept, for you to exactly like play with encoder decoder. But if we're going to be talking about the real problems, yeah, then just having diffusion as the idea itself already would work. It's important that nobody makes you to 1,000 steps. Make it less, yeah. So this is very important, yeah. As data scientists, you need to understand like, what is the edge? Because, you know, let's be honest, even some colleagues, some very experienced colleagues, they sometimes, for example, solve toy problems with, I don't know, LLMs, yeah, large language models, which makes no sense. Which just makes no sense. I mean, yes, you're going to solve the problem, yeah, but you're going to burn resources, you're going to lose time, and nobody needs it. So that's why just be wise in terms of exactly if you need some simpler over there. So that's why I would say that the gradation is that bias are not even the easiest, yeah, the fastest to train. Yeah, the GANs, they are harder to train, but still they can give you a good result, and diffusion models are just already too good. Sorry, I think maybe this is the last one. Maybe this is the last one. So let's see. Boom. What is the drawback of ultra-aggressive models compared to diffusion? So you have seen diffusions. Yeah, we were discussing that ultra-aggressive going to be iterating like one by one. So fidelity. What means fidelity? Fidelity means that you are going to have some inconsistencies, like, for example, cat with two heads or cat with two tails. Yeah, lower sampling speeds. We discussed it. Yes. So like what means to speeds. Then diversity, it means as what we were discussing on GANs, yeah? So it means that it's going to be just generating something very similar. So, and here there is diversity. So drawback of ultra-aggressive, yeah? So we mentioned now ultra-aggressive, it's like pixel by pixel. And there is, so what would be like the obvious? I would say, like, think about the most obvious. If you're generating pixel by pixel, or if you're generating whole stuff at once, like what should be and drawback of ultra-aggressive? Ooh, everybody was managed to answer. So, and boom. Okay, good. So, as I said, this just go for the most obvious because, in fact, it's true. If you are just going pixel by pixel, the problem is that at some point you might just lose the context of what is happening. Yeah, because your image is in fact something that is kind of 2D, yeah? So I would say that maybe here is the main problem, that this is something like 2D, and it's better to be generated like everything at once, yeah, at some region, yeah, but not just one by one. That's why ultra-aggressive models can easily give you a cat with two heads. So just because we're generating, and it occurred that there are going to be one cat, and maybe they're going to be like part of another generating, but even didn't finish, yeah? So, and lower diversity on high resolution images? No, I mean, it has nothing to do with diversity. So diversity means, as I said, that exactly when you are starting just generating the same and the same. No, ultra-aggressive models, they're quite rich. So just given different inputs, it would still be able to be very diverse. And it doesn't matter if it's low resolution or high resolution. But fidelity, yeah, it's going to be a problem. So, ooh, wow. Fabio, congrats. So you are getting the not open beer at home. So this maybe you can all do it. But that's fine. I mean, because Laura, you were not on time at one. Oh, Jesus Christ, such a pity. Oh, but Fabio answered 5 out of 6. Man, come on, are you joking? How you did it? How you did it? But what is the hardest question? Moderate. Really, the first one was the hardest one. Come on, guys. After that, we had such questions, and the first one was the hardest. You are monsters. I'm telling you. No, this is something. Okay, good. Congrats. Congrats. That is cool. So Fabio was the most silent, but yeah, exactly. Just was doing a job. I see. I see. But that's okay. That's okay. I know how it is done. Others are asking questions, and you remember the answers to the questions. Yeah, this is how it works. But no, guys, really, you did a wonderful job. I'm just looking at this stuff, and when you initially told me that you're gonna have AI courses in the future, my expectation was zero, yeah, with the variance of zero. So I was expecting that, okay, it's going to be maybe zero. But no, you definitely outperformed. So, but this is for you. I would say that mainly I have already mentioned all of these concepts, but for you to remember, yeah, how the current generative models work, that you can mix them. This is first. So as I said, for example, VAE with this flow, or you can, for example, do the cascading models. So what is it? Very important trick. It means that you are just taking your, let's say, diffusion model. That is, I told you that one option is to generate like a small cat and then to make like the enlarging and sharpening. But there is another opportunity to make this enlarging also with help of diffusion. So you are taking like a little cat and then you are trying to then input it to another diffusion that trying to enlarge it, and etc. etc. This I would say the first idea that is there. It comes from the pro-GAN. It's called the model pro-GAN. It's because it's progressive GAN. So this is the GAN that is continue generating bigger, bigger, and bigger pictures. Yeah, from the initial. Let's say I think initially it generates like 2 by 2 pixels. Then it gives like more, more, and more. So adding more and more details. So basically, this is one of the ideas. So mixing between the models and also the same type of models. Then encoded decoder, as I told you, basically plays a large role because it's feature abstraction. It's coming to low dimensionality, meaning that work much faster. Your model is gonna work much faster. Also, here you see, I'm saying here, it's very important, yeah, that don't be afraid to split your big model into submodels. For example, as we discussed in style GAN, yeah? So preferring some model which is giving as an input this noise, and then the main model is strength, yeah? Or for example, this sharpening and scale. This also works. And this one may be, let's say, again, a bit like weird because we didn't discuss today at all the attention mechanism, but just attention, this is the heart of these autoregressive models now. And I mean, again, this is more about do not hesitate to mix the stuff. So it means that this idea, it means that, for example, when you are generating your picture, yeah, you might look at some particular parts of your picture, yeah? And this is exactly what attention is responsible for. This is such a mechanism that was also revolutionary when we were first getting into the era. I think it was first with long short-term memory models. And basically, yeah, there it was used. Now, for example, you can, where this DALI is making the generation of text to image, because it basically not simply taking the noise and then generating image. It's taking noise and description, yeah? And then it converts noise and description to some image. There, this network that we have seen that has also convolution 1 by 1, it is using their attention, for example. Also, there is very popular, I think, from 2021 diffusion model with transformers. So yes, exactly. I mean, this is, you are scientists. Data science is not about data analytics. Data science is about science. And scientist is the one who says, no, I don't trust you. This is not how it works. Or I want to try it differently, yeah? Or whatever. So freedom. Freedom is what makes Switzerland the best country in the world and which makes data science the most interesting job. Yeah, so that's why this is the main outcome. Okay, so basically, I think that's it. I mean, this is the one just, I mean, I understand now we're not many, but this stuff is, for living questions. If you have questions and you're afraid to ask them, you can, yeah, basically this. But now you can ask whatever questions if you still have them, yeah, or please.
the diffusion model,
Yes.
you said it takes maybe 1,000 steps, or how many steps of noise you include. That's why it's not very good for generating the pictures. But can it be used to enhance existing pictures?
It's no. Having 1,000 steps means that it is, let's say, could be a little bit slower than you expect.
Mm-hmm.
This is not in terms it's not good. No, vice versa, it's good. Yeah, you have added a lot of noise. It means that basically you can be very variable in generating something because you had so many steps of adding noise. It means that when going back, you could generate whatever doc you want. Yeah. So this is kind of the stuff. But about enhancing something, this also works. And for example, diffusions, they work quite well in such a called in painting. In all this stuff, where you have a picture, you can remove part of the picture and say, for example, that I want to have now, for example, I don't know, the cat was sitting on a dog, yeah? Now you say that I want now another dog sitting on a dog, yeah? And you are exactly saying in which area this will. This one, because you see, this is going to be kind of also like the empty area, which is in fact going to be first initiated by noise behind the scenes, and then the dog going to be pretty. But yes, very nice thing. Yeah. Okay. Question?
Yes. So a bit of a layered question, but it's if you look at AI generated images, usually by stable diffusion without whatever, then if they're trying to look photorealistic, what is usually done is that they have some blurry background that usually comes from the camera to simulate that effect, but they're often too perfect, especially the blurry part is way too perfect. Yes, and before you mentioned that you have like the initial image, you shrink it, then you blow it up again, and then you sharpen it. So is that why? That'd be an explanation why it looks too perfect, because if you sharpen the image, that then you basically lose information, you don't add in noise anymore. Could that be why they look too perfect?
No, no, you're absolutely right. They look too perfect because of this sharpening post-processing. Yes, this sharpening is used, I think, now in all of these data images. And basically, I understand what you're saying. Yeah, that they look absolutely. I mean, it's clear that this is not done by person. Yeah, let's say that this is definitely was done by machine. But this is how it was constructed. So because this was their initial aim, they wanted to have it very sharp and high resolution. You can take this model and let's say corrupt it a little bit. So I mean that if you want the person realistic images, yeah, you can do it. You can do it exactly like you can exactly a little bit change the sharpening procedure, make it not as sharp as possible. Yeah, you can exactly, for example, train this blurring, exactly the blurring procedure, for example. Like, yeah, exactly. Questions, but you know how to reach me out. I mean, you have seen in the presentation what I'm called. So if you have another questions, please feel free to contact. And as I said, the presentation going to be sent. And yeah, I'm really happy that you came today because it helps you in your future researches. Because researchers, absolutely. Okay, cool. Then I think now we can stop recording because then it was, where can I stop it? Sorry. Stop recording. Yes, stop it because now